I thought it's a nice picture, just because I'm talking about oracles, but also because we have a nice memory. A bunch of us were at a conference several years ago in Delphi, and we had a great time there. So I thought it'd be nice to remind ourselves of that. This is joint work with Junlai Go, who's in Singapore currently, and Iskander Kalimulin and Joe Miller. Okay, so now let's see. So I'll start by introducing enumeration reducibility, as usual. We say that A is enumeration reducible to B if there is a program that transforms any enumeration of B into an enumeration of A. And here, by an enumeration, I mean just a function on the natural numbers with range B. So that's an enumeration of B. In this definition, we can show that we can always choose this program to have a specific form. It can be chosen to be a C table of axioms that all have the following form. If you see this finite set x1 through xk in B, then enumerate x in A. The reason that I want to point this out is I want to draw your attention to a relationship to the relation C in, which can also be defined in a similar fashion. So we can say that A is C in B. If there's a C table of axioms, which are almost exactly the same, except here we have two finite sets. We ask that one is a subset of B and the other a subset of the complement of B. And if we see that happen, then we enumerate X in A. So you can, the relationship between these definitions that is apparent just from the form of their definitions is stated in this proposition. A is C and B if and only if A is reducible to B joined with a complement of B. And in contrast to the relation C in, the relation enumeration reducibility is actually transitive. So that's one advantage of asking for the same kind of information positive on both sides from the oracle and the reduced set. The relation is now transitive, so it's in a natural way we can associate to it a degree structure. This is the structure of the enumeration degrees. And again, the same proposition now allows us to embed a copy of the Turing degrees into the enumeration degrees. We'll call these the total degrees. So we map the Turing degree of a set A to the degree of A joined with a complement of A. And right, so that's our setting, enumeration reducibility. Now let me talk about relativizations. So when we relativize a class of objects with respect to a Turing oracle, we usually replace CE, wherever C appears in the definition, by C in. Let me give some examples to support this general statement. Okay, so for example, we can say that G is A generic. If G meets or avoids every set of strings, W, where instead of, so one generic would be W is C, A generic, we ask that W is C and A. Similarly, we can talk about a sigma 01 in A class. This is now a collection of members of Cantor space X that all extend some finite binary string in a set W, and W is CE in A. Okay, so in order to relativize now to an enumeration oracle, we make this very natural replacement of everywhere we see C and A, we replace it by enumeration reducible to A. So following these two examples, we will get the notion of A generic sets. So where A here is treated as an enumeration oracle, so generic relative to the enumeration oracle A. So this is if G meets or avoids every set of strings that is enumeration reducible to A. And I'll use these brackets surrounding A to denote that the use of A as an oracle is as an enumeration oracle rather than a Turing oracle. And the second one, we can talk about sigma 01 relative to an enumeration oracle class. the definition is straightforward. So I'd like to point out that both of these are not new ideas. Generic relative to enumeration oracle, the first time I saw that was in my first ever course in computability theory, in which my dad just introduced it as the most natural thing. And it surprised me later to find out that neither enumeration reducibility nor generic relative to enumeration oracle are standard and taught in every first computability course. And then sigma 01 relative to enumeration oracle classes, we use those with Joe to study a notion of randomness relative to enumeration oracle. Maybe some of you have heard me talk about that, or him. So today we're going to discuss the relation PA above, or PA relative to enumeration oracle. Okay, so let's recall the definition and see how we relativize it. So for Turing oracles A and B, we'll say that B is PA above A if B computes a member of every non-empty pi01 relative to the Turing oracle A class. So now we need to relativize pi01 relative to Turing oracle A to an enumeration oracle. And we already did this for sigma 01 classes, so we can do this for pi01 classes very naturally. P is a pi01 relative to enumeration oracle A class, if and only if it's the complement of a sigma 01 relative to enumeration oracle A class. And I'd like to point out here, first of all, that we're looking at closed sets in Cantor space. We're just kind of changing how they relate to oracles slightly. In particular, all the pi01 classes relative to Turing oracles appear as well, but now they're relative to A join A complement. And we're treating the elements of such a set as total objects. So in particular, when I say that B enumerates a member of P for some pi01 relative to A class P, what I mean is that there is some X in P, some member of the class, such that B enumerates both the positive and negative information from X. So it enumerates X join X complement. Now we're going to be relativizing PA above. So a justification for this, if you like, is that if we have that P is a pi01 relative to A class, then so are also the sets of all complements of members in P, or the join of X and X complement for X and P. So it doesn't really matter. We wouldn't gain anything by just asking, by not treating these members of pi01 relative to A classes as total objects, because the total objects will appear there in the list as well. Okay, so finally we can give our definition. B treated as an enumeration oracle is PA relative to A treated as an enumeration oracle if B enumerates a member of every non-empty pi01 relative to the enumeration oracle A class. Okay. Now, all that I've said so far, let me just point out that it follows that this relation extends the relation PA above, but when we switch from Turing oracles to their enumeration degree representation. So B is PA above A if and only if B join B complement, treated as an enumeration oracle, is PA above A join A complement. So in a sense, we're taking the image of the relation PA under the embedding of the Turing degrees into the enumeration degree. So that defines now a relation on the total degrees, and we're extending it to all enumeration oracles. Okay, so now the questions that we want to examine is what classes of oracles behave well with respect to this extended relation, and what classes of oracles do not behave well, are there such? And by behave well, we mean similar to what we already know, so similar to the Turing degrees or the total degrees. And one natural class to look at in this situation is the class of the continuous degrees. These were introduced by Joe Miller to capture the algorithmic content of points in computable polar spaces. So I could give you a definition that goes through certain terms in computable analysis, but I'm not going to need it. So I'll give you an equivalent definition, a characterization that will actually be used later in the slide. But let me just say that they form a proper, in fact, definable subclass of the enumeration degrees, and they properly extend the total degrees. So they sit between the image of the Turing degrees and all the enumeration degrees. And it's natural to wonder what their properties with this relation are, because we already know that they behave well with respect to the relation PA in particular. We know that non-total continuous degrees have this interesting property that the set of total degrees that they bound is a Scott set, which means that it's a Turing ideal, so closed under, closed under less than and join, that's clear, but it's also closed under the relation PA. And furthermore, for total degrees X and Y, we know that Y is PA above X if and only if some non-total continuous degree is between them. So this allows us actually to prove that the image of the relation PA, so the relation PA that we define, but just restricted to the total degrees, is actually a definable relation as well. This is not very important to the talk, but I like to think about definability, so I point these things out. But in the process of defining, well, actually showing that the continuous degrees are definable and the enumeration degrees, Andrew C. Guza, Joe Miller, and I proved a characterization of the continuous degrees that will be the one that's very useful for this talk. And it is the following. So we show that A has continuous degree if and only if it is codable, which means that there's a non-empty pi01 relative to A class, and I'll call this CA, and I'll use CA in the next slide. So remember, CA is a codable class or coding class. Such that every member of CA uniformly enumerates A. So there's one procedure that relative, when you plug in as an oracle any member of this class, you get an enumeration of A. Okay. So, as I said, continuous degrees are good oracles because they have all these, well, the following three properties that also all total oracles have. The first one is that if A has a continuous degree, then A can't be PA relative to itself. And the proof is very simple. So if A enumerates, so if A is PA relative to itself, A would enumerate a member of every pi01 relative to A class, in particular this coding one, CA. But then if A enumerates a member of CA, that member enumerates A back, so A is equivalent to that member, so it's a total set. But that can't happen for total oracles, right? In the Turing situation, you can't have that a set itself enumerates a member of every pi01 class relative to itself, just because you can relativize the construction of a tree with no computable path. So there you go. Second, if A has a continuous degree and B is PA relative to A, then A is bounded by B. So B can enumerate A. And what we'll call in this case, we'll say in this case is that A is PA bounded. If it's below every oracle B, that is PA relative to it. And this is, again, very easy to see just from this codability property. So if B is PA relative to A, B enumerates a member of the coding pi01 class, but that member enumerates A, so by transitivity, B enumerates A as well. And then the third one is that there's a universal pi01 in A class. So there's a non-empty class relative to pi01 relative to A class, such that every member of that class enumerates, is PA relative to A. So this is true of Turing oracles for sure. So if we're just thinking about the relation PA relative to Turing oracles, then if you take all the diagonally non-computable functions relative to that oracle, that forms a Pizeron relative to that oracle class. And every such function allows you to build a path in any tree that has an infinite path, because it allows you to kind of figure out where the dead ends are. Okay, so we use this idea, but we kind of join it up with the idea that that A is codable. So to get a universal class for a continuous degree A, a set of continuous degree A, we'll take the coding class and we'll join up every member X with a function F that is DNC2 relative to X. So now a member of that class, so now every non-empty Pizeron relative to A class is going to be a Pizeron relative to X in the normal sense, the Turing sense class, because X enumerates A, and X is a total object. And the DNC2 function relative to it will enumerate a member. So this gives you now a universal class. All right, so continuous degrees have these nice 3 properties. Are there any oracles that don't have these 3 properties? They seem fairly natural, and you know, when a person starts working with the relation PA, trying to prove more complicated things about it, one is kind of, it's easy to assume that oracles have these properties until you stop and think, wait a minute, is that a given, or am I using something total here? Well, it turns out that there are bad oracles. So early on, and this was many years ago, in fact, with Joe Miller, we showed that there are actually self-PA degrees. So when we're looking at enumeration oracles, we can have fixed points of the relation PA. And in order to convince you of this, rather than just stating the theorem, I thought I'd prove it to you, because the proof is, well, sketch the proof really. But the proof is fairly easy, and I think I can go through it pretty quickly. So we're building one of these self-PA degrees. And suppose that at stage S, we have determined the first k many columns of A completely. We've determined all the bits. So what do we do next? So at stage S, so by star AS, let's denote the maximal possible set that we can extend this construction to be. So given the fact that we first fixed the first k+1 many columns. So we fill in every other column by omega. Okay, so now we're dealing with the ETH Pizeron class relative to A. And notice that no matter how we build A, it's going to be a superset of this maximal possible A star set, right? Because, well, the larger the set, the smaller the class, right? So this is the A star is the largest possible set that A could end up being, so that corresponds to the smallest possible Pizeron class. Well, if that is finite, if that class is finite, the smallest possible one, then by compactness, there's going to be a finite subset of A that makes the class empty. Okay, so if this smallest class is empty, then some finite subset of A makes it empty by compactness. Well, we'll just take this finite set A, and by filling out some finely many more columns, we can ensure that E ends up being a subset of A. So the ETH enumeration, the ETH Pizeron class relative to A is empty. We don't have to worry about it. Otherwise, if it's non-empty, then well, it is going to be a subclass of our class. So enumerating a member of this subclass is enough. And this set PE relative to A star, it's just a non-empty Pizeron relative to the first k+1 many columns class in the Turing sense. So what we do here is fill in the next column by a set that's PA relative to the first k+1 many columns. And we're done. So now we can enumerate a path in this class, and hence we can enumerate a path in PE relative to A, whatever A ends up being, because that will be larger. Okay, so self-PA degrees exist, so they're bad oracles. They violate the first property. They also violate the third property. If A is self-PA, then A can't have a universal class. And this is, again, fairly easy to see. If A is self-PA and P is a universal class, it's a Pi-0 relative to A class, so A enumerates a member in it. Now let's think about this member X. X enumerates a member of every Pi-0 in A class, but every Pi-0 in X class, where we treat X as a Turing oracle now, is a Pi-0 relative to A class, because A enumerates X join X complement. But then if X is PA relative to A, X has to enumerate a member of every Pi-0 in X class, but we know that can't happen. Okay. So we have good oracles, we have bad oracles. We don't quite know what happens with the second property. In particular, do self-PA degrees violate all three nice properties? Can they be PA bounded? Or can they be PA bounded? And we don't know whether this having a universal class applies only to continuous degrees or maybe to a larger class. So we want to see where the boundaries are. And the first question we can answer completely. So it turns out that PA bounded is actually another characterization of the continuous degrees. And this was proved when Johanna Franklin came to visit us. So a big group of people with Stefan Lemp, Joe Miller, and Noah Schweber. So we showed that the continuous degrees are exactly the PA bounded enumeration degrees. And the proof idea, I won't say much about it, but let me just point out that codable here is, again, very, very useful. So the general idea is that we build a kind of nested sequence of Pi-0 relative to A classes. Every new class, every smaller class has the property that every member of that class computes a path in all previous non-empty Pi-0 classes. So when you take the intersection, you'll get something that is PA relative to A. But also, using the fact now that A is not codable, we can, by moving to a smaller class, we can diagonalize against the ETH enumeration operator enumerating A. So any path in the smaller class enumerating A via the ETH enumeration operator. Okay, so this kind of brings, well, it answers the first question. Self-PA degrees can't be PA bounded because they're disjoint from the continuous degrees, but it brings the focus to the second question. So we're wondering now, can non-continuous degrees have universal classes? Are there other ways to have a universal class? And here it turns out that the answer is yes. There are other ways. So here's a definition. Let's say that an enumeration oracle A is low for PA. If every set that is PA, just in the Turing sense, just any old PA set, well, its total version is PA relative to A. Okay, so first of all, let me point out that total oracles can't be low for PA. In fact, they can't even bound any non-zero total degree because, so if A is low for PA and it bounds a total degree X join X complement, then just singleton X is a Pi-0 class. And from the definition of low for PA, it follows that every PA degree computes X. But there is a minimal pair of PA degrees, so X has to be computable. So low for PA oracles have to be quasi-minimal. They can't bound any non-CE, well, non-computable total set. in particular, this means that it's a new way to be to have a universal class, and they have universal classes, right? Because any PA degree is PA relative to them, and there is one Pizeron class, the DNC2, the classical DNC2, diagonally non-computable zero unvalued functions, is going to be a universal class for any low-for PA oracle. Now, before I show to you that there are such things, other than zero, well, non-zero, low-for PA degrees, with Junlei, Kalimulin, and Joe Miller, and so this is the group that did all the rest of the results that I'll mention, well, most of the rest of the results that I'll mention in this talk, so I'll abbreviate them to GKMS from now on, but that's the group. So we gave a nice characterization of when an oracle is low for PA. That is useful. So it turns out that A is low for PA if and only if every non-empty Pizeron relative to A class has a non-empty Pizeron subclass, so unrelativized. So, right, clearly if it does, then the PA degree computes a member of that Pizeron subclass. And so clearly if an oracle has this property, it's low for PA, but the reverse is true as well. Okay, so now using this property, we can give examples of actual non-zero oracles, non-C oracles that have this property are low for PA. In particular, every one generic degree has this property, and for those who know, this is halves of non-trivial K pairs also have this property. And the proof is very simple. So I'll prove one, because we know what generic degrees are. I don't need the definition of K pairs, so I won't give it. But okay, so fix a one generic G, and suppose that the ETH enumeration, the ETH Pizeron class relative to G is not empty. Okay, now take the C set of finite strings relative to which the ETH Pizeron class is empty. Okay, well, G can't meet this set, it has to avoid it, so there will be some finite initial segment of G that has no extension in W. So no matter how we extend sigma, we can't ever make the ETH class relative to that extension empty. Well, take the maximal possible extension. So this is a similar idea that we saw before. So take sigma followed by 1, 1, 1, 1, 1, put in everything maximally as possibly as you can. So this now is a non-empty because of our choice of sigma. Non-empty, it's a Pi01 class because this is, right, a computable object. And it is because G is a subset of the set with characteristic function sigma 1, 1, 1, 1, 1, it is going to be a subset of P relative to G. Okay, so this is the picture we have so far. We've got not self PA at the top, total at the bottom, a universal class is here in the middle, two ways to be a universal class. And we know that they're definitely different because, well, continuous contain total and non-zero low for PA implies plus minimal. We don't know whether these two arrows are stripped. So at this point, Kalimulin was reminded by some work that he did with Pozorenko. And this, I don't intend for you to read the definition, that's why I've grayed it out, but he defined a bunch of notions inspired by properties from descriptive set theory. So this is the reduction, uniformization, and separation property. These first three are all take the set of sets, enumeration reducible to an oracle X, and ask that that set of sets has the corresponding property, if you're familiar with it from descriptive set theory. And then two more properties that are more computably theoretic and use these tools in their work. So he had all these properties, and the theorem, he managed to classify all these oracles, how they relate to each other. And the theorem well, he and Pozorenko did, of course. And what they proved, what they showed is the following picture. All these arrows are strict. And notice that this is remarkably similar to the picture that we had before, with total and quasi-minimal at the same spot. So 4 new classes, total and quasi-minimal at the same spot. So we were wondering, is there a reason for this? And is there some relationship between these two notions? And it turned out that there is. So I'll go through each of these notions and we'll see how they match up with the ones we talked about already. So first, the reduction property. That is the least related, but nevertheless, it's fun, so let's talk through it. So we'll say that X has the reduction property if whenever you have two sets A and B enumeration reducible to X, you can find disjoint sets enumeration reducible to X such that A0 and B0, such that A0 subset of A, B0 subset of B, and the union is all of the union of A and B. So the reduction property turns out to be equivalent to the uniformization property that was at the slide, which I probably should have removed, but and oracles with the reduction property exist. For example, one very easy example is Kleini's O has this property. The reason is that, well, if a set A is enumeration reducible to O, if and only if A is pi1, 1. And we know that pi1, 1 sets have the reduction property, so there you go. So this example in particular, if you know a little bit more about continuous degrees, shows you that the reduction property and continuous degrees are disjoint. Not disjoint, sorry, incomparable. Not disjoint, but incomparable. So there's no relationship there, even though that's where, that's the same place in the diagram was held by those two. But there's still a relationship to what we were talking about, and it can be seen as follows. So suppose we want to construct a pi01 relative to an enumeration oracle X class U. So, so suppose we want to construct a universal class. So we want to construct it so that if the eth pi01 relative to X class is non-empty, then the eth column of U somehow codes a member of the eth pi01 class relative to X. So the kind of standard way we would approach it, if X were a total oracle, for example, is that we would fix an enumeration of the set that defines the eth pi01 relative to X set class. So we'll fix some enumeration of that set. And then we'll put in A all pairs E sigma such that all members extending sigma 0 are kicked out of the eth class first relative to that fixed enumeration. And put the pair in B if all members extending sigma 1 are kicked out first. So this first is important because it keeps our sets A and B disjoint. So now we can take a separator for A and B, and that will give us a universal class. But if X is not total, we don't have a notion of first. We can't at all talk about what happens first. So we can't use first. So different enumerations of A and B will make different events happen first. So as a result, we can't avoid having A and B intersect. So for sigma, we'll have, if sigma in particular has no extensions in P, we'll be forced to enumerate it at both sets A and B. But then the reduction property will allow us to solve precisely this problem. It will take these sets A and B that intersect where it doesn't really matter, and it will give us disjoint subsets. Well, disjoint sets, one subset of A, one subset of B. Now a separator for that will give us a universal class. Okay, so that's how the reduction property is used. let's move on to the next one, the separation property. So X has the separation property if for every pair of disjoint sets A and B, there's a separator C below X. So every pair of sets A and B that are disjoint and below X, there's a separator such that, well, the separator here again is treated as a total object. C joint C complement is below X. So we'll have A as a subset of C, B as a subset of C complement. That's a separator. Now notice that the set of all separators C for sets A and B that are disjoint forms a pi-0 relative to X class. So we actually used this in the previous slide, but let me state it here. And in fact, let me isolate these kinds of classes by giving them a name. So let's say that a pi-0 relative to X class P is a separation class if it's precisely of this form, the set of all separators for disjoint sets A and B below X. And let's call these sep-X classes for short. Okay, so now just a restatement of the separation property brings highlights a nice analogy that we had to a previous property. So we can just say that X has the separation property if and only if X enumerates a path in every sep-X class. So if we just restrict from all pi-0 relative to X class, just the classes, just to the sep-X classes, just to the separation classes, then the separation property is exactly like self-PA. In particular, if X is self-PA, X will have the separation property. So we can think of separation property as an analogy to self-PA, but restricted to just sep-X, separation classes. Okay, so it turns out that the next property, the computable extension property, also has a similar analogy to a previous property. So the definition here is X has the computable extension property if every partial function with graph reducible to X has a computable extension, of course, possibly also partial. Okay. And here I see that I have the sign backwards. So it's an extension. Psi is an extension of phi. Okay, so we show that the following are equivalent. X has the computable extension property if and only if X has the extension property with respect to 0, 1 value functions. And this is not new. This trick was already used by Pozorenko and Kalimulin in their work. So not too interesting, but technically useful. So now using 2, we can show that it is equivalent to the following property. So if A and B are disjoint sets reducible to X, then there are disjoint C sets. So they're still disjoint, but A is a subset of C and B is a subset of D. Disjoint C sets C and D. So it's kind of like extending a function below X to a computable function. We're taking A and B, but extending them to CE sets that are still disjoint. Now this is easily seen to be equivalent to every set Y with PA degree computes a member of every separation class relative to X. And so now again, we have this analogy. Computable, X has a computable extension property if and only if you restrict to just separation classes, we have that every PA degree computes a member of those. So it is the analogous property to low for PA, but just for separation classes. In particular, if X is low for PA, then it has the computable extension property.
Could I just ask a question here?
Yes.
This somehow reminds me of effective inseparability. If you can't do that, this extending.
Yes. I haven't thought about how effective inseparability you mean.
Yeah, but you know, you could, when you say you can't do that.
Yeah.
But anyway.
Okay.
Sorry.
It's good. It's good to, yeah, it's a good thing to think about. But off the top of my head, I can't tell you what the relationship there is exactly. But okay, so we have two of the properties in the diagram relate to two of the corresponding properties at the same positions of our previous diagram, but by just restricting to just SEP-X classes. And then here comes a mystery that that we didn't know how to solve for a while. So the universe, having a universal function property, and let me just say what this is quickly. So X has a universal function. If there's a partial function, you would graph reducible to X, so that every partial function with graph reducible to X appears as one of the columns of U. So this property should somehow correspond, be an analog of having a universal class, but we couldn't quite see how. And finally, we solved this by, as I say, as the title of my slide suggests, by introducing a little bit of uniformity. So we defined a universal Pizeron relative to X class to be a non-empty class whose every member is PA relative to X. In other words, every member of P enumerates a path in every non-empty Pizeron relative to X class. So we will adjust this definition slightly by adding some uniformity. So we'll say now that we'll ask that in addition to what we had before, if we have a class Q that is non-empty, then there's one procedure that produces a path in Q relative to every member of P. So I'm saying here a little uniformity because I could have asked that also the function that takes the index of Q to the index of that uniform procedure is somehow effective. I'm not, so I'm not asking that. I'm only asking that there is one procedure. And this doesn't change anything we've discussed so far. So in all cases that we've seen so far, the total degrees have this, we have this extra uniformity. So the total degrees have even the further uniformity that I mentioned, the larger one. The continuous degrees have it as well because the codability is also uniform. Low for PA degrees have it, reduction or close with a reduction proper. So all things that we've talked about have this extra uniformity. But now with this extra uniformity, the mystery is solved because we have that X has a universal function if and only if X has a universal with respect to 0, 1 valued functions. Again, this equivalence just uses the same trick. Nothing, no new ideas here. But that turns out to be equivalent to having a class relative to XP such that there's a uniform procedure that produces a path in any SEP-X class, separation class Q, relative to every member of P. So having a universal function becomes really the analog of having a universal class, but with respect to just computing members of separation classes. And in fact, this class can itself be chosen to be a separating class. Okay, so briefly, how does 2 and 3 relate to each other? So to go from 2 to 3 is fairly easy and fairly standard. So suppose that you have a universal function U, then P will just be the separating class for these two disjoint sets. EX such that U of EX is 0, EX such that U of EX is 1. So here's where we're using that we have a 0, 1 value function that's useful. So if A and B are disjoint sets reducible to X, then A times 0 and B times 1, the union of this is a graph of a partial function with graph reducible to X. So it's the column of the universal function for some index E. Well, then the eth column of any path in P will allow us to compute a separator for A and B. Okay, so to prove the reverse is more tricky. So suppose that we're given this class P and we want to define the universal function. So here's what we'll do. We'll define U of the pair EY x to be equal to Y. And here I have to tell you what I'm thinking of when I write this pair EY. So think of E as the index of the graph of the 0, 1 valued function phi that we want to copy in this column. And I is going to be this uniform procedure that allows us to compute a separator for the values that on which phi gives 1 and the arguments on which phi gives 0 from every member of the class P that's given to us. Okay, so now we'll define U of EY x to be Y if and only if, well, we see that XY really is in gamma EX. So if gamma EX really is the graph of a function, then it's the correct function where everything is fine. But the second line here allows us to still have a function even when gamma EX is not the graph of a function. So it kind of gives a confirmation using the Pi01 class, and it uses compactness here. It asks for a finite set D such that the Clopin set defined by D is covers all of the Pi01 class P. And also there is an N such that all strings that are of length N and extend members of the finite set D have agree on what the value of this procedure that was given to us by the index I relative to oracle. So all these sigma relative to oracle sigma on X agree on the value Y. So the second part will prevent us from having here, oh gosh, I see that I'm running out of time quickly. Okay, so the second part will ensure that we actually have a function, and using compactness, we show that we'll actually have this finite set whenever we've correctly guessed the indices. So every function will appear as a column in U. So this is the picture we've got so far. I've talked about all of the forward directions. We have these pairs of analogous notions. We have low for PA and computable extension, and right, so the inside notions are the analogs when you restrict to just separating classes, and the outside are for all PA degrees. And introducing these, finding these classes inside solved the open questions we had at the previous diagram, along with proofs that all the arrows that you see in this diagram are actually strict. And I'll try to be quick here. I'll skip a proof, but let me just tell you, we use the same kind of forcing notion to get all these separations. So let me briefly describe what the forcing notion is. So we treat omega, we identify omega with finite strings that have the following form. So on 0, you have 2 possible values, 0 and 1. On argument 2, you have 4 possible values. On argument 3, you have 8 possible values, and so on and so on. So it's a computable tree that branches more and more as the height of it grows. So a forcing condition is going to be a finite tree of this form, a finite subtree of this fast branching tree of a fixed height. Epsilon is going to be a rational in the interval 0, 1. And we'll think of a condition as associated, as approximated approximating a finite set, which will be the complement of the tree within the strings that we're considering. So if you have two such conditions, we'll say that S delta is stronger than T epsilon if and only if, well, S extends T, so up to height T, it's exactly the same, and then maybe it grows a little bit further. Delta has to be less than or equal to epsilon, so the rational is shrinking. And we have a restriction here. So on the branches where S was not determined because it has to extend T, so we could cut off a few, right? We were not forced to extend in all possible directions, but we're forced to extend in at least 1 minus epsilon, at least a 1 minus epsilon proportion of the immediate successors. So we're not allowed to trim the tree too much. So a filter in this partial order will be associated to a big tree, which is the union of these trees that we're building. And correspondingly, it will define a set, AG, which is the complement of that tree, or equivalently, the union of these ATs that we associated to the conditions in the filter. Okay, so now if G is sufficiently generic, then AG must have the computable extension property. And to see this, so suppose that let's fix a forcing condition T epsilon and a pair of enumeration operators gamma 0 and gamma 1. So first we try to force gamma 0 and gamma 1 relative to the generic object to intersect. And if they intersect, we don't have to worry about anything. If they don't intersect, we would like to prove that we can extend our condition to ensure that these two sets are separated by disjoint C sets, because that was one of the equivalent characterizations of the computable extension property. Well, it turns out that just halving the epsilon is exactly such an extension, because if you let C0 and C1 to be the corresponding set of all n's such that some condition extending this new one T with half of the epsilon, so all n's that some such condition puts in, has n enter in the corresponding gamma 0 relative to AS or gamma 1 relative to AS. Okay, so those two now are CE, right? Whether there is such a condition as CE to C. And they're disjoint, because if we assume that they're not, if we assume that there's some n that gets put in both gamma 0 and gamma 1 relative to some S0 and relative to some S1, then because we only used epsilon divided by 2 in both cases, so we were limiting the amount of extensions we're cutting severely, we could just take the intersection of the two trees, and now we have only cut out an epsilon proportion of them. So this now gives us a condition that extends the original condition and contradicts the assumption that we couldn't force to make these two sets intersect. Okay, so that was pretty quickly, hopefully you got something out of it. By a more well, elaborate and difficult analysis, we can also get that sufficiently generic G's also produce sets that don't have a universal class. And by combining this first forcing construction that we had when we showed that there are self-PA degrees, weirdly enough, we can produce a set A that has the separation property but is not self-PA. So these are all of the separations. So this is my picture again. In conclusion, I have these several open questions. The first of all is this extra uniformity that we added at the end necessary? In many cases with enumeration degrees, enumeration reducibility, it turns out that you get some uniformity for free. But in this case, we weren't able to show that you get this one for free. We tried. The second one is more technical. So when we're thinking of moving from a universal class to universal separating class, there are various moving parts here. So we can just restrict to computing paths and only separation classes. We can also restrict to looking only at the universal classes, ensuring that they are separation classes. So the only kind of combination that we couldn't place, well, we know that it's strictly stronger than others, but we couldn't kind of figure out where exactly it belongs, is the one that, well, an answer to this question would give it to us. So if A has a universal class, does it always have a separating class as well that is also universal? So this is kind of, in all the examples that we've seen, this is true, but we don't know if this is the same as just having a universal class. It might be stronger. And finally, so we know that the relation PA is definable when it's just restricted to the total oracles. Is it definable in general? This is a question I threw in there because I'm interested in those kinds of questions. All these diagrams were built using a tool that Ludovic and Joe have constructed and is available on Ludovic Pate's webpage. So you can go there to figure out how to build your own diagrams. So thanks very much, and I'm sorry for going over time.
Okay, thank you very much for your talk. Is there any question? Please don't forget to unmute yourselves.
So maybe again, this I'm still struck by the getting universality from the looking for separators with that strong property that you had, which does look like in the setting of completions of PA. So they're the same degrees, they're recursively isomorphic to the separators for effectively inseparable pairs.
Right.
For the effectively inseparable pairs means you can extend it in a way that looks similar, except you're in the enumeration reducibility sense. You're adding something more to your sets effectively.
So you're thinking that that might be an insight to getting an answer to 2, the second question?
Maybe. So I just wonder. Yeah. So I think maybe it was a result of Mariya Soskova, that this recursive isomorphism between the completions of PA and the separators of effectively inseparable pairs. So somehow this seems, well, I mean, I don't know.
Thanks. I mean, it's certainly worth thinking about. Thanks for pointing it out there.
Okay, any other question?
I have one. The fact that having the reduction property and being continuous are two disjoint notions.
Not disjoint, incomparable.
Yeah, sorry. Yeah, that's what I meant. That follows from Pliny's O being
right. So Pliny's O can't be cototal because its complement is sigma 1 1. So and every continuous degree is cototal. So that's one direction. And for the reverse direction, Puzarenko and Kalimullin showed that the class of total degrees bounded by an oracle that has the reduction property has a stronger property than the continuous degrees. It's not only closed, it's not closed under the relation PA, but it's closed under the jump. So it's a jump ideal. So that's the, yeah. Thanks for that question. It allowed me to sneak in something I couldn't fit in the talk.
If I may follow up on that, does the latter result show that having both the reduction property and being continuous is still a strictly larger class than being total?
I don't know. That's a good question.
Thanks.
Oh, yes. Now I just realized I was muted, and I was always reminding everybody not to be muted. So let's. So thanks again for your talk. If there is no other open question, other question, and so as you know, there is a tradition of breakout sessions. So where we can split into smaller rooms and have casual chats. So